Okay, in question number 15, this is also about money, so I'm going to be very careful about beginnings of years and ends of years. At the beginning of the year 2000, there is a machine bought by a company for $15,000. Each year the value of the machine decreases by 20% of its value at the start of the year. It's an odd sort of thing where it waits until the start of the year before it falls. But anyway, so an example is at the start of 2001, it's now worth 15,000 times 0.8. At the start of 2002, it's worth 15,000 times 0.8 squared. Okay, so that's just me writing out the first three terms of the sequence to get in the groove, and as it happens I've actually just answered part A, which is to show that the start of the year the value of the machine was 9,600, so 0.8 squared times 15,000, yep, equals 9,600. Okay, part B. When the value of the machine falls below 500, the company will replace it. Find the year in which the machine will be replaced. Okay, so I'm going to assume that this sequence can actually hit 500 at some point. No, it probably won't. It'll probably skip 100. It'll go like from 550 pounds to 490 pounds. But there's nothing to stop me solving the algebra that governs this sequence equal to 500, so that's what I'm going to do because it will give me some insights. So the algebra for this is Tn equals a r n minus 1, because it's certainly a geometric. We're just multiplying by 0.8 each time, that's the r. The a is 15,000, and the n is the number of terms in the sequence. I've got 3 so far, and that's the mystery for us. But I do want the sequence to spit out a 500. So 500 over 15,000 equals 0.8 to the power of n minus 1. So the power you have to put on a 0.8 to get a 5 over 150, which is the cancelling of this, is n minus 1. So I type that into the calculator. This calculator doesn't have a log button. I need to use a log 10. This is a change of base law. So let's go log 5 divided by 150. Oh, wait on. Yep, that's log 10. Divided by log 0.8 equals 15.2. So n equals 16.2. So, so 16 terms, it's above 500. At 17 terms, it's below 500. Now link this back up to this. So the number of terms written out seems to be always one more than this indication of the year. So when that's a 2, there's 3 terms. So when there are 16 terms, that will be a 2015, and that's when it's a little bit more than 500, 510 say. And when that's a 2016, This will be the 17th term, which we've just discovered is a little bit less than 500. And remember, these are always starts of years. So in which year does it cross the 500 mark? It must be 2015, because at the start of 2015 it's 510. That's completely made up. I've just done a random figure that's a little bit more than 500. That's why I wrote the word say. At the end of 2015, in other words when 2016 starts, it's a little bit less than 500. So therefore the year in which it fell below 500 is 2015. This again demonstrates the exceptional care that's required to make sure you get your N right, and writing things out neatly so you can make sure you're doing the right thing by looking at your method for big numbers and checking that it works out on the small numbers, like early on in the sequence. When you're confident it works out early on in the sequence, you can apply it later on in the sequence. That's what I was doing when I was comparing this number here to the number of terms we've had. Remember, n in this machinery here is the number of terms you've had. That may or may not always link perfectly with how many years you've had in a question. Now, what about part C? Okay, to plan for a replacement machine, the company pays £1,000 at the start of each year into a savings account. The account pays interest of 5% per annum. The first payment was made when the machine was first bought, and the last payment will be made at the start of the year in which the machine is replaced. Using your answer to part B, find how much the savings account will be worth when the machine is replaced. So, how many terms? So this is the machine, and this is the savings. So that's the machine, and what I'm going to now draw here is the savings. Okay, so there's no way I'm going to have enough room to write that out. So the machine is so 2000, 2001, 2002, all the way down to 2015. These are starts. So initially it's 15,000, then it's 15,000 times 0.8, which I think is 12,000, and then 9,600. Okay. Now what about the savings? At the start of the year, they put in a £1,000. And at the start of 2001, that £1,000, the night before, has received a 5% boost. And on that very day of the 1st of January 2001, another 1,000 is put in. After a year, at the start of 2002, that original 1,000 gets another boost of 1.05. That 1000 has now been there for a year, so it gets another boost. And then finally, there is a 1000 put in, okay, which hasn't had a boost yet because it's only just been put in. It takes a whole year before you get paid your interest in most institutions. So let's just work out how this relates. It seems to me that the number indicating the year is the same as the power, and the number of terms is one more than that. So if that's a 2, then this power is a 2, and there will be 3 terms. Which means in 2015, there will be 1000 to the power of 15 plus 1000 times 1.05 to the power of 14 plus. There will be 16 terms. If there were 3 there when there was a 2 there must be 16 here when there's a 15 there. And the last term will be 1000 because it always was when we were tracing it through on the simple examples. Now, I'm just thinking, do I need to do this again for 2016? What have I actually been asked? Find how much the savings account will be worth when the machine is replaced. Okay, so the machine gets placed at some point in 2015, and all these amounts are there throughout 2015 because it takes a whole year before they give you an extra amount of interest. So this is the amount on the first day of 2015. It's also the amount on the second last day of 2015. And we already decided that it was going to get replaced during 2015. So this is the amount of the investment. Now what is that? That's a geometric sequence. Its A is 1000. Its R is 1.05. And its N is 16, which is very carefully worked out. So therefore, the sum of that investment will be 1000 1.05 to the power of 16 minus 1 all over 16 minus 1. You pump that through a calculator and you get the answer. Okay, question 16. There's a mortgage that's taken out for 80,000. It's to be paid by annual instalments of 5,000, with the first payment being made at the end of the first year that the mortgage is taken out. Interest is paid 4% on any remaining debt. Find the total time taken to pay off the mortgage. Okay, so I'm going to be very careful here. Year 1, year 2, start, end, start, end, start, end. Okay, so at the start of year 1, so we're going to call all these figures what you owe. Okay, so at the start of year 1, the moment you take that money, you owe 80,000. And at the end of the year, it is suddenly worth 80,000 minus 5,000. I'm not going to write 75 yet because not doing the arithmetic sometimes helps you keep track of a pattern. Okay, now, I mean, I might regret that. I might wish in 1 minute's time that I'd written a 75,000 there, but for the moment I'm just going to write minus 5,000. Now, that night, you get charged 4%. So 80,000 minus 5,000 times 1.04 is what you owe. And then at the end of that year, So that's what you... So, wait on. This is what you originally owe. Then at the end of the year you pay 5,000, which reduces it. But then immediately the bank says, oh, you haven't paid it all back. So they then boost what you owe by 1.04. And that's how much you owe until the end of the year. When you reduce it by another 5,000. The very next morning, they go, you didn't pay it all back. So they take what you owe, which is this, and then they boost it by another 1.04. Then at the end of the year, you reduce that by 5,000. Okay, I think that's enough examples to get my head around it. Now, is that anything to do with this chapter? Is that a geometric sequence? It looks pretty grim. But maybe if I expand it, it'll look better. So 80,000 times 1.04 minus 5,000 times 1.04 minus, so that's that, here's a minus 5,000, that's that, but this is all being times by 1.04, and then a minus 5,000 is being taken off. Now I'm going to expand it again. 80,000 times 1.04 times 1.04 again. Here this 5,000 times by 1.04. This 5,000, however, has just a single 1.04. And then at the end, there's a 5,000 that doesn't have a 1.04 on it at all. Now, this looks like a mixture of two things. So let's say in year 20, looking at this pattern, that's a 3 and this is a 2. When that was a 2, well, I haven't expanded the other ones, but I'm pretty sure I can guess that the 80,000 is boosted by one fewer 1.04s than the year in which I'm tracking it. So in year 20, it'll be 80,000 times 1.04 to the power of 19. And then we're going to have a whole bunch of 5,000s. Now I'm actually going to put a bracket with a -1 there. That's going to be, this was always the same as that. Now how many of those were there? There were the same number of these 5,000 businesses as the year number. So this will have this will have 20 terms. Which means this is a classic example of a question that mixes together two things. This 80,000 business is just a geometric sequence, whereas this stuff in the brackets is a geometric series. But either way, we've just concluded that at year n, what you owe is 80,000 times 1.04 to the power of n minus 1 minus 5,000 times 1.04 to the power of n plus 5,000 times 1.04 to the power of plus all the way down to 5,000 times 1.04 plus finally a 5,000 that hasn't been boosted at all, and that will be n terms. Which means what you owe is this grand formula here. It's 80,000 times 1.04 to the power of n minus 1 minus, this is a geometric sequence, I'm going to imagine it starts there and ends there. So the first term is 5,000, the common ratio is 1.04. The number of terms is n. Now, this will be fun. We have to work out when that is equal to 0, because our actual job is to find the total time taken to pay off the mortgage. Goodness me. Okay, so let's do our best. Logarithms are going to be involved, I'm pretty sure. $5,000. I was going to do 5,000 divided by 1.04, but that'll be a pretty horrible decimal. I don't want to mess things up like that just yet. We need that to be 0. In other words, we need 80,000. I'm going to divide both sides by 1,000. Just to keep it nice and neat. I'm going to times everything by 1.04 because I hate fractions. Here I'm just adding the powers. There's a power of 1 there. You times that. N minus 1 plus 1 will be n. Now I'm going to expand this. Now going to collect like terms there. Oh, that's not a 1.04. It's a 1.04 minus 1. Sorry. Damn. Okay. Right, well. I'm going to times everything by 1.04 minus 1. What a hassle. and times everything by 1.04. I don't really know what I'm doing here. Okay, I'm going to treat that as 1.04 to the power of n times an extra 1.04. Okay, I've been trying to avoid actually picking up the calculator, but I don't think I can avoid it anymore. That's a 78. That's an 80. So we've got 78 lots of 1.04 to the power of n minus 80 lots of 1.4 to the power of n. So therefore we've got negative lots of negative 2 lots of 1.04 to the power of n. Fairly sure I made a mistake here, and the reason is because so this thing here, 5 times 1.04 it's 5.2, so 1.04 to the power of n equals 5.2 divided by negative 2, and you cannot get a negative number by powering up a positive number. So I've clearly made a mistake.